let's start with a new chapter, energy of a system. You know, the objective here is to study the motion of any object, is to calculate the position, the acceleration, and the speed or the velocity at a time t. When it was impossible to use or to calculate A, we used Newton's second law, F equal ma. We calculated A and we came back to the kinematics equations to find the value of x and t and v. Maybe also we have, sometimes it's impossible to use Newton's law and the kinematics equations to study the motion of the object. We have to find another method like the energy of a system to find some parameters like the velocity. So by using the energy of a system, we can find V. When you find V, we can calculate the acceleration. We can find the position at a time t by using kinematics equations. So the energy of a system is a new method. It's a help to study the motion of a system to find the velocity. For example, we can find the kinetic energy of a system equals to half mv squared. If you have the energy, you can calculate V. If you have V, you can calculate the position and the time by using kinematics equations. Here, in general, the application of this method can be on a single object or a particle, or it can be applied to a collection of objects. You can say the kinetic energy of a object equals to half mv squared. If the system contains two objects, A and B, so the total kinetic energy of the system equals to half mva mva squared plus half mvb squared. So you can apply this method of any number of a object. Now I want to start with the new topic, the work. In order to have a displacement, in order to move any object, we have to apply a energy. Okay, so the work is the energy needed to move any object. The notation of omega as definition equals to the force applied on the object times the displacement. Okay, this is the general equation, general definition times the displacement. Let me start directly with a simple problem. How can we calculate the direction of omega if F is applied with the displacement, if F is applied is opposite to the displacement, and the details of the work? Let's take a simple object. Here we have an object A of mass m. We apply F. We have a kinetic friction small f, and we have the weight of the object and the reaction n. So here we have small f, mg, n, and f. To calculate the total work applied on the object equals the work exerted by small f by mg by n, and here I advise you to write f in terms of the components. We have fx and fy. Even mg, if mg has two components, you write omega mgx plus omega mgy. Okay, let's draw. The line of motion is to the right, so here we have fx and fy. Okay, before I will give us a general definition. Any f perpendicular to the displacement has no work. Okay, this is a general definition because I don't want to waste your time. Okay, you have to solve quickly the problem. Any f, if you have the displacement in the right direction, any f perpendicular to this displacement has no effect, has no work. We can cancel its value directly. You see here the displacement, the displacement depends only on the initial point and the final point of the position. Let's say here we have an object initially at the position 1 and finally at the position 2. The displacement is a simple vector from the point A, from the point 1 to the point 2. Here we have the displacement. Here we have only a displacement in terms of x-axis. So it's equal to delta x in the I direction. We don't have y displacement. So it's equal to the final position. We can say x2 minus to the initial position x1 in the I direction. Okay, x2 minus x1 is the distance, not the distance. In this case, is the distance because we have a direct motion between 1 and 2. Okay, let's now, first of all, I want to calculate omega f equals f is opposite to the displacement. Okay, so we have to write minus. After you put its value F times the displacement x2 minus x1. Okay, it's simple, just like this. Minus and plus, if the F is applied in the same direction with the displacement, you put plus. If F is opposite, you put minus. So equals to minus the F equals to mu times n, you know, equal mu static times n, okay? And x2 minus x1, you can calculate its value easily, okay? Okay, omega mg equals to omega fy equals to omega n equals to 0. Why? Because they are perpendicular to the displacement. Okay? Because mg fy and n are perpendicular to the displacement. Here we have the displacement to the right, and n is up, mg is down, and fy is up. So here we have mg, here we have n and fy. The angle equals to 90. So we don't have any motion in this direction. You can cancel them directly. Okay, we have also, okay, we cancel fy, mg, n. We have fx, omega fx equals to fx has the same direction with the displacement. So we write plus fx times the displacement. Okay? Equals to, you know, here, fx, we have an angle theta here. If you take this triangle, you can say cosine theta equals to fx over x over f. So fx equal f cosine theta. You can say here equal f cosine theta times the displacement. Listen here. You don't need to put absolute value. Now, just to say, take the positive value of f and the displacement, okay? And you put minus and the plus. It depends the direction of f. If f is with the displacement or its opposite. I can give another example. So here we can write the total work done. Omega f equal minus mu s n x2 minus x1, 0, 0, 0, and fx equals to f cosine theta x2 minus x1. Okay, this is the general formula of omega. We can have another example to explain how can we apply. Look, we can have a inclined plane. Let's say here we have an inclined plane. Initially, here the applied F, we have the weight mg. Let's say here we have the motion upward. Okay, here is the initial position, and here we have the final position, position 1 to the position 2. So we have the displacement in this direction. Okay, this is a displacement. Now the motion is up, so this is the line of motion, the positive direction, and here we have y-axis. Here y and x. Let's apply F on the object, and the motion is going up on the inclined plane, so the kinetic friction will be down. Okay, and we have a reaction N. So here we have F kinetic, N let's say N. Okay, so F has two components. Here we have F. We have to draw the components of F. We have Fx and Fy with the line of motion along x-axis. Okay, here we have the displacement. We have only one dimension. Let's say displacement here is dx equals to x final minus x initial equals to x2 minus x1 equals to d. Okay, d. As direction, it's up. Okay, we can say like this. As magnitude, we have d. Okay, we have F and N. Here we have N, Fx, Fy. Mg also has two components. We have Mg y and Mgx. Okay, Mg x and Mgy. Here we have Mg. We have N, we have F, Mgx, Mgy. Okay, it's all. Now I want to calculate the total work applied on the object to move or to get a displacement delta x, and we have a displacement, a distance d. We can say the total work applied on the system equals omega f plus mg x plus mgy fx fy fx fy, and we have n. Okay, we have f mgx mgy fx fy and n. Okay, now we begin with f. You know, f is opposite to the displacement, so it's negative, minus. And as value is what equals to f equal mu kinetic times n, okay, times the displacement d. mgx is opposite to the displacement, so omega mgx equals minus mgx times the displacement d. You know that mgx equals to mg sine theta, the angle of the inclined plane. So we can write mg sine theta times d. Okay. We have also fx. Fx is in the direction of the displacement, so it's positive. So omega fx equal plus fx times d. Okay, now you come to this triangle here. Let's say here we have alpha. Cosine alpha equal fx over f, so fx equal f cosine alpha. So fx equal f cosine alpha times d. And okay, we calculated f mgx fx, mgy, fy, and n are perpendicular to the displacement. So omega of fy equals to omega of mgy, omega of n equals to 0 because they are perpendicular to delta x. You see here, delta x, we have mgy is down, the angle is 90, n is up, also the angle is 90 between them, and we have fy also, the angle between them equals to 90. We can write the final omega total equals to omega f equal minus mu kinetic times n d minus m g sine theta times d plus F cosine alpha times D. This is the total work done on the object. Okay. Now, if I want to calculate any one, for example, if I want to calculate n, okay, to calculate just one minus omega f equal minus mu kinetic times n times d. Okay, so we have the coefficient as a given value. We have the distance, so we have to calculate n. To calculate n, you have to do the projection in terms of y-axis. Okay. We have to do the summation of f. You know, the summation of f y equals to 0. Okay. You can write in general the equation. You can write Newton's law, F plus N plus F plus mg equals to ma. Okay, to calculate n, you have to calculate in terms of y-axis. So in terms of, here we have f minus I, okay, the negative direction, fx in the positive direction, we can say fx I. We have fx and we have f. Mgx in the negative direction minus mgx I. N in the positive direction, mgy in the negative direction. I think we have fy also, plus fy in the positive j direction equals to ma. Okay. To calculate n, we have to take only the y is a j direction. We have n up minus m g y equal and we have fy plus fy equals to 0. Okay, so n equals to mgy minus fy. You know, mgy in this case equals to mg cosine theta. Okay, so we can write equals to mg cosine theta minus fy. Here we have fy equals to f sine alpha. F sine alpha. This is the value of n. Okay, so omega f equals minus mu kinetic times n, which is equal to mg cosine theta minus f sine alpha. This is n value times d. Okay. Okay, by the application, when we do some application, you can understand well with a numerical value. You can calculate all these parameters. Okay,